What we are going to be discussing today is the concept of mesh analysis. This is the crutch upon which many of you will lean to pass this class, in my opinion. It is a very powerful circuit analysis tool that, for whatever reason, you guys seem to prefer over using nodal analysis. I'm going to guess it's the lack of fractions. That's really the only thing I can think of that makes it any easier than nodal analysis. It is very, very similar to nodal analysis in as much as we are going to be setting up systems of equations and solving them. But instead of applying Kirchhoff's current law, this time we're going to apply Kirchhoff's voltage law. Okay. So the first circuit that we are going to analyze looks like this. We have a 10-volt source, a 9-ohm resistor, a 2-ohm resistor, a 4-ohm resistor, a 1-ohm resistor, a 3-ohm resistor, let's call this 2 VX voltage source, an 8-ohm resistor, a 5-ohm resistor down here, and a 6-ohm resistor here. And let's make this relatively easy on you. Let's say that Vx will be the voltage drop over our 4-ohm resistor. So the first step in a mesh analysis problem is to identify our meshes. This is arguably, that's not how you spell identify, arguably even easier than identifying our nodes because there's not a lot of potential ambiguity. Right? So if you recall from our very first meeting in this class, a mesh is simply a loop or a closed path that doesn't contain any smaller loops. So in this case, there are going to be exactly 3 meshes. And our first mesh is going to be around this path. Our second mesh is going to be around this path. And our third mesh is going to be around this path. There is no reference quantity in mesh analysis. So we're going to go ahead and move along to assigning mesh currents. And so what I'm going to do is I'm just going to put an arrow on the end of my loop there, and I'm going to call this mesh current IA. I'm going to put an arrow on the end of this loop. I'm going to call this mesh current IB, and I'm going to put an arrow on the end of this guy and call it mesh current IC. So the way that I have drawn my mesh currents represents them flowing in a clockwise direction around each mesh. It does not matter if you choose to express your mesh currents in a clockwise direction, in a counterclockwise direction, or some combination thereof, but I would argue that you should be consistent in only using one direction because it makes the math less confusing. I have heard tell from, I think, some of the mechanical engineering students that they prefer to do their mesh currents in the counterclockwise direction because it's the same direction as your second moment of inertia or something like that. I don't particularly care one way or the other, but I am going to choose to use a clockwise direction for all of my mesh currents. Okay. All right. So let's talk for a moment here about the concept of these mesh currents. Okay. So if we look at the 10-volt source, what's the mesh current that's flowing through that particular element? IA, right? IA is flowing into the negative polarity terminal and out the positive polarity terminal. What about the 2 ohm resistor? So mesh currents IA and IB are flowing through it. Dylan suggested that it was IA minus IB, but that really depends on what direction that we're looking for the voltage drop over as to whether we express it in that way or not. So in a moment, we're going to start writing our Kirchhoff's voltage law equations. And effectively, we're going to follow one mesh current around its path. And we're going to assume that the mesh current that we're following is flowing into the positive polarity terminal of all our resistors. And any mesh current that's flowing opposite will be flowing into the negative polarity terminal of our resistors, which will tell us the signs that we need to have in our KVL equation. Okay. I'll go over that in a little bit more detail in about a minute and a half. Our third step here is where our real analysis begins. We need to express controlling variables in terms of our mesh currents. And I always move this step pretty close to the beginning because it is easy to forget to do. So in this case, our mesh current is the voltage Vx, which is the voltage drop over the 4 ohm resistor with positive polarity terminal on top. So we're going to say that Vx is 4 ohms. What mesh current, excuse me, is flowing into the positive polarity terminal? IA. And what's the mesh current flowing into the negative polarity terminal? IC. So using Ohm's law, Vx is then 4 ohms times the total current flowing through that 4 ohm resistor, where IA, since it's flowing into the positive polarity terminal, gets a positive sign, and IC, since it's flowing into the negative polarity terminal, gets the negative sign. Are we okay with that? That's the convention that we are going to adopt to write any voltage drop. All right, so step 4 here will be to perform KVL around each mesh. So at mesh A, what I'm going to do is I'm going to start in the bottom left-hand corner because that's my place that I typically start for all of my Kirchhoff's voltage law equations, and simply follow that mesh current IA around its clockwise path and observe all the voltage drops I see. So the first thing I see is the negative polarity terminal of the 10-volt source. So that's going to look like negative 10 volts. The next thing I see is a 9 ohm resistor. And the only mesh current that's flowing through it is IA. Stylus will write. Then I see the 2 ohm resistor. And since I'm following the current IA around, that's going to get the positive sign. And mesh current IB is flowing in the opposite direction through the 2 ohm resistor. So I will have minus IB. Then I have the 4 ohm resistor that has a total current of IA minus IC. And finally, I have my 5 ohm resistor, which just has a mesh current of IA. Since I have ended at the same node that I started from, I set this equal to 0, and I'm done with that particular KVL equation. So the rules for writing our KVL equations here are the exact same rules that we used to write KVL equations previously. The only thing that we're really paying attention to here is the direction of our currents, which are going to tell us what our sign should be when we look at the total current flowing through any particular element. All right. For mesh B, I'm going to start in the bottom left-hand corner, which is right here, and follow that current IB around its clockwise path. So what's the first thing I see? 2 ohm resistor, okay. IB minus IA, absolutely right. So when we're following mesh current IB around, it should get the positive sign, and mesh current IA is flowing in the opposite direction, so it gets the negative sign. What's the next thing we see? The 1 ohm resistor. And what's the total current carried by the 1 ohm resistor, Davis? Exactly right. So it'll just be plus, my stylus will behave, 1 ohm times IB. What's the next thing we see? Pardon? All right, so what's the voltage drop over the dependent voltage source? Say it louder, Sarah. 2Vx, okay. Do we see the positive polarity terminal first or the negative polarity terminal? Positive, so it'll be plus 2Vx. Thank you, ma'am. And the next thing we see, the 3 ohm resistor. I know that this is boring. Some of you aren't as familiar with this, and that's okay. So what's the total current flowing through the 3 ohm resistor? IB minus IC, thank you. And since we've wound up at the same node that we started from, we set it equal to 0. Then we would move along to KVL at mesh C. Starting here at the bottom, we have 4 ohms times IC minus IA. Then we have our 3 ohm resistor carrying a current of IC minus IB. Then we have our 8 ohm resistor carrying a current of IC. And finally, our 6 ohm resistor carrying a current of IC as well. If we substitute our Vx relationship into our KVL at mesh B relationship, this becomes a 3-equation, 3 unknown system, and we can all solve it using our calculators. So let's take a few minutes to do that now. So for my first equation, the coefficient for quantity IA is 9 plus 2 plus 4 plus 5. The coefficient for The variable IB is simply -2. The coefficient for variable C is -4. And the constant term will be +10 when I move it to the other side of the equal sign. In my second equation, my coefficient for IA, I'm going to have -2 from the first term. The 2Vx term is going to give me +2 times 4, so that's +8. And there are no other IAs. For IB, I'm going to have 2 + 1 + 3. And for IC, I'm going to have 2 times -4, so that's -8, minus an additional 3. And my constant term there is 0. And for my third equation, my coefficient for IA is -4. My coefficient for IB is -3. And my coefficient for IC is 4 + 3 + 8 + 6. And my constant term is 0. So when I solve this system of equations, what I find is IA is equal to 465 milliamps. IB is equal to -410 milliamps. And IC is equal to 30 milliamps. Everybody else get similar results? Good deal. Okay. So once we know these three mesh currents, we can then easily determine every voltage drop in the circuit. And from that, then any power absorbed or supplied by any element in the circuit as well. So mesh analysis serves as a good starting point to fully analyze really any circuit that contains more than one mesh. All right. How did we feel about that particular example? Anything seem wild or particularly difficult? All right, so let's do something similar to what we did in Wednesday's class and mess things up by including current sources. Okay. So here is our new circuit of interest. We're going to have a 3 ohm resistor here. A 4-volt source here. A twice IX current controlled voltage source here. We have a 5 amp source here. 2 ohm resistor here. 5 ohm resistor through which a current IX flows. Here is a 4 ohm resistor. Here's a 6 amp source. And then up here is a 10 ohm resistor. All right, so as before, step 1 will be to identify our meshes. So here is one mesh. And because I've already told you explicitly that I am going to make my meshes be clockwise currents, I'm going to go ahead and put the arrow on it. Here is mesh 2, or what will be mesh 2 in a moment. I'm now going to label my mesh currents. So this will be IA, IB, IC, and ID. And actually, I'm just going to move this guy. There's no confusion there. Step 3 will still be to express our controlling variables in terms of our mesh currents. So in this case, we are trying to express the quantity Ix, the current flowing up through the 5 ohm resistor, in terms of our mesh currents. Anybody care to take a stab at that? ID minus IC, absolutely correct. So for those of you who maybe are unsure, what we did here is we looked at what mesh current was in the same direction as it flows through the 5 ohm resistor. So around its clockwise path, ID is flowing in the up direction when it sees the 5 ohm resistor. So that's the same direction as Ix. So it got a positive sign. And the mesh current IC, as it travels around its clockwise path, when it's going through the 5 ohm resistor, it's going in the down direction, which is the opposite direction of Ix, which is why it got the negative sign. So it's always the current flowing in the same direction minus the current flowing in the opposite direction. All right, thank you, John. So step 4 will be to express our current relationships in terms of mesh currents. And so what I mean by this is every current source will in turn have a current relationship. So this circuit has 2 current sources, right? There is a 5 amp current source, which I'm going to call an interior current source because it's on the inside of the circuit. And every interior current source should be a combination of 2 meshes, okay? So what 2 meshes touch the 5 amp current source? Yeah. So IC and IA touch the 5 amp current source. IC is flowing in the same direction through that middle branch. IA is flowing in the opposite direction through that middle branch. So we'll have IC minus IA. We also have a 6 amp current source. This is a perimeter current source because it's on the outside edge of the circuit. And every perimeter current source will be able to be expressed in terms of a single mesh current. So this one is going to be ID because that's the mesh current that touches the 6 amp source. And it's positive ID because the mesh current is flowing in the same direction as the current source. If we had a 6 amp current source direction up instead, we would find that 6 amps is negative ID because the mesh current is flowing in the opposite direction. Okay. So interior current sources are always going to be a combination of two meshes. Perimeter current sources are always going to be expressed in terms of one mesh current. All right, so step 5 is going to be write KVL equations for all meshes. I'm going to put an asterisk by this because we are about to see that this doesn't quite work out when we have an interior current source, okay? So we are going to make a minor change to this momentarily. So the problem here is going to arise when we get to trying to express the voltage drop over the 5 amp source, right? So if we follow that red mesh current around its clockwise path, eventually we are going to have to take the voltage drop over the 5 amp source. The problem there is that the 5 amp source has a current of 5 amps flowing through it and a voltage drop of whatever it needs to have in order to make the rest of the circuit behave correctly, okay? So this is very similar to the problem that we ran into with trying to find the current through a voltage source, and we are going to adapt in much the same way, okay? So what we're going to do here is we are going to have, let me do it in purple, a super mesh. And what the super mesh does is it combines the two meshes which touch our interior current source and provides a path that goes around the current source so that we never wind up taking the voltage drop over that current source explicitly. Now, in this particular case, and I've drawn it this way for a reason, if we write our super mesh loop around meshes A and C, we also wind up avoiding the voltage drop over the 2 ohm resistor. That's perfectly okay, okay? All we're really doing with this super mesh technique is writing a KCL equation around mesh A, writing a KCL equation around mesh C, and then adding those two mesh equations together. Because if Kirchhoff's voltage law around one loop is equal to 0, and Kirchhoff's voltage law around a second loop is equal to 0, 0 plus 0 is equal to 0. Since we are following currents in different directions, the voltage drop over that 2 ohm resistor is going to cancel out because we're going to add it both ways. So it's perfectly okay for us to avoid that voltage drop in our super mesh equation, because if we had included it, we would be including a positive version of it and a negative version of it anyway that would cancel each other out. Okay? So I'm going to amend this and say for all super meshes, so if we start here, what's the first thing that we see? We're following the purple path around, right? Okay, so we see a 10 ohm resistor. And what mesh current is flowing through the 10 ohm resistor? IA, absolutely right. What's the next thing that we see? 4 ohm resistor. What's the mesh current flowing through our 4 ohm resistor? Exactly right, IA minus ID. What's the next thing that we see? So since we're following the purple path for the super mesh because we're trying to avoid that current source in the middle of the circuit, The next thing we see is the 5 ohm resistor. Absolutely right. What's the total mesh current flowing through the 5 ohm resistor? Exactly right. IC minus ID. So at this point in the circuit, we are following the current IC around its path. And so IC is going to get the positive sign. That's 5 ohms. IC minus ID. What's the next thing we see? Minus 2IX. So that dependent voltage source. What's the next thing we see? 3 ohm resistor. Absolutely right. And it's carrying a current of IA minus IB. Wonderful. All right. Step 6 will then be to write KVL equations for the remaining meshes. I'm going to put an asterisk around this guy too, because we're about to run into a small problem here that we've actually already taken care of, okay? So if we look at mesh IB, everything is going to be hunky-dory. Right? So if we start at the bottom left-hand corner, we're going to see minus 4 volts plus 3 ohms, IB minus IA plus 2IX is equal to 0. Are we all okay with that? So I said minus 4 volts plus 3 IB minus IA plus 2IX. We all groovy there. All right. When we try to write a Kirchhoff's voltage law equation for mesh D, we are again going to try to come up with a voltage drop over the 6 amp current source, which is problematic. How many unknown quantities do we have in this circuit? So we have our 4 mesh currents, IA, IB, IC, ID, and then we have that controlling variable IX, right? So it stands to reason in order to solve this system, we would need 5 equations. Here's 1, 2, 3, 4, and 5. It turns out we don't need a KVL equation for any mesh that contains a perimeter current source, okay? It's impossible for us to write one in the first place, and we already have enough equations to solve our system. So anytime we have a perimeter current source, so one that's on the edge of the circuit, we will only have a current relationship equation. We will not have a Kirchhoff's voltage law equation. Anytime we have a current source on the interior of a circuit, like the 5 amp source, we will have both a current relationship equation and a SuperMesh KVL equation, okay? If we were to solve this guy, get to those results real quick. Slightly too far. We would find that mesh current IA is equal to 33 over 19 amps. Mesh current IB is equal to 203 over 57 amps. mesh current IC was equal to 128 over 19 amps, and mesh current ID was 6 amps. Okay. All right, so the last thing that I want to do here, and I'm going to give you guys a fairly trivial circuit that we're going to look at, is what happens when we have multiple current sources in a circuit and they kind of mess things up. So what I mean by that is, let's say that we have the following circuit where we have a 10-volt source, and then we have a 3 ohm resistor, 3 amp source, 5 ohm resistor, 1 amp source, and then an 8 ohm resistor and a 2 amp source, like so. I'm going to identify my mesh currents. So this is going to be 1, 2, and 3. Call it IA, IB, IC for the sake of argument. And I don't have any controlling variables. Now I'm going to write my, actually, okay. So I was going to say, let's skip that step, but let's not, because I don't want to get you guys in the habit of skipping the steps when I'm telling you explicitly to do it in a certain order. Okay, so for our 3 amp current source, what is our current relationship equation? IB, that's a terrible looking B, minus IA. What about our 1 amp source? IB minus IC. And what about our 2 amp source? Negative IC. We have 3 equations and 3 unknowns. We don't have to write any KVL equations here, okay? So if, this is the point that I'm trying to get here. If we have an interior current source that touches a mesh that contains a perimeter current source, we don't have to write a KVL equation. Effectively, it's all lumped together with perimeter current source space relationships, right? So if we looked at this circuit and we tried to write a KVL equation around any of these meshes or any combination of these meshes, we cannot, because it will always include the voltage drop over a current source. Okay, it's not something that you're going to see a lot, but it is something that you're going to see in the in-class assignment you're about to start working. So I wanted to make a point of it here, okay? So just to be very explicit here, if we considered only SuperMesh BC here, right? I'm calling it SuperMesh BC because there's an interior current source between meshes B and mesh C. SuperMesh BC contains a perimeter current source, which means we cannot write a KVL equation. We could really consider this whole thing SuperMesh ABC because there is an interior current source between meshes A and B, and there's an interior current source between meshes B and C. Well, SuperMesh ABC contains a perimeter current source, which means there is no KVL equation that we can use to solve here. All of our mesh currents we would determine just by manipulating these three current relationship equations. Okay. All right, that's enough out of me for today. So you've got an in-class assignment to get cracking on. Let me know if you have any questions.